The IceCube Neutrino Observatory is one of the world's largest, most impressive science experiments, and it exists in one of the most inhospitable places on Earth, the South Pole, Antarctica. In my last video about IceCube, I talked a little bit about what it is, why it exists, and how it works, but today I want to talk about how they built it. And I don't mean this building right here with the supercomputer inside of it. That was relatively easy. The hard part was drilling holes in the Antarctic ice sheet over a mile deep and placing thousands of sensors for the experiment to work. It took a dedicated team over 7 years to do. Let me show you how they did it. The entire IceCube drilling operation centered around one concept, the hot water drill. This is just what it sounds like. You pump hot water into a hole in the ice until you get it as deep as you want, and then you pull it out. But while the concept is simple, the execution is not. You've got to melt water from the snow, heat it up to boiling, pump it a mile deep into the ice, and do it all at 200 gallons a minute. To help make this job easier, the drill was outfitted with lots of different sensors. If the water coming out of the drill tip wasn't hot enough, the drillers knew to slow down. If the drill tip actually hit ice, they knew to stop for a while. They even had this ingenious device to measure the diameter of the hole as it went. This was crucial to make sure that the hole was big enough for the long line of IceCube sensors that would be going in after the hole was drilled. To make things more complicated, you can't use the hot water drill until you get about 150 feet or 45 meters deep. That's because there is a top layer here called the firn, which really is just hard-packed snow that hasn't turned into ice yet. Unfortunately, the hot water drill relies on water pooling in the hole to continue melting it and making it bigger, but in this top layer, water just leaks out into the firn. To conquer this problem, a special Firn Drill was needed. This drill has a small nozzle at the end to get the hole started, but the main part of the drill is a cone of copper pipes that are pumped with boiling hot water. This ensures that minimal water is wasted, but that the hole gets made to its proper diameter. But where is all this hot water coming from? One of the many challenges of this project is the fact that nothing comes for free at the South Pole. Every drop of water has to be melted, and every bit of heat has to be created. For this massive operation, water has to be melted from the ice through the use of a Rodriguez well, or rod well for short. This could be a whole video on its own, but a rod well is basically a system of injecting hot water deep into the ice sheet, which melts the ice and creates a large bulb of meltwater. This meltwater can then be pumped up to the surface for use. Pretty much every major Antarctic station on the interior of the continent uses this system for obtaining fresh water, including the Amundsen-Scott South Pole Station. After reaching the surface, this cold water from the rod well is then stored in large container tanks. These container tanks also have a backup water source available, snow, dumped directly into the tank by a bulldozer. If something goes wrong with the rod well, the bulldozer can provide enough water to prevent the drill operation from shutting down in the middle of drilling a hole. As I'll explain later, preventing shutdowns is a big priority for this operation. After the tanks, the water passes through an array of high-pressure pumps, which provide all the pressure needed to push the water through the rest of the system. After the pumps is the boiler array. This array consists of 35 fuel-burning water heaters. The water passing through them is heated up to 190 degrees Fahrenheit, or 88 Celsius, which is the boiling point of water at the South Pole. The boiling point of water goes down as you go up in altitude. Boiling water takes a lot of energy, especially when you're starting with very cold ice, and this system needs to provide boiling water at 200 gallons or 750 liters per minute. Altogether, the boilers create 5 megawatts of heat energy, or 16 million BTUs per hour. That's the energy needed to power about 3,000 homes in the USA, or about 7 times the normal energy needs of the South Pole Station. After the boilers, the water runs out to the tower operations site. It first loops through the massive hose reel, which contains over a mile of hose, and then onward to the drill tower. The drill tower sits over the current hole being drilled, but it is built on skis for mobility. This is important because after drilling a hole in the ice and placing the IceCube sensors, it needs to move quickly to start setting up at the next drill site. In a harsh environment like the South Pole, with its limited working season and its capricious weather, speed is a valuable asset. After the boiling water is injected down at the drill head, it slowly rises to the top of the ice sheet as if from a spring, melting the sides of the hole as it goes. Once it reaches the Firn Layer, however, it starts leaking out. To prevent this water from being wasted, a submersible pump is placed just below the Firn Layer. It captures this return water and pumps it all the way back to the holding tanks. One interesting fact is that the hot water hose used for the drill wasn't strong enough to support its own weight, and needed to be attached to the much stronger support line. Since these two lines were on separate rolls, they had to be attached at the point of entry into the hole. The drillers found that the best way to do this was with glass cloth tape wrapped around both lines. Unfortunately, this also meant that the tape needed to be removed every time they took the drill out and reapplied for the next hole, but apparently this was the most reliable solution. After each hole was drilled, the drill and submersible pump were removed and the hole was ready to be filled by a string of digital optical modules. These are the sensors of the IceCube Neutrino Observatory and are responsible for detecting neutrinos deep in the Antarctic ice. 60 of these digital optical modules, or DOMs, are lowered on a cable into each hole, with the deepest one going to a depth of about 1.5 miles or 2.5 kilometers. The lowering operation needs to be done quickly, as there is only a matter of hours to get this done before the water in the hole starts to refreeze. This refreezing problem is why there are multiple backups and redundancies in the systems, like the bulldozer that can dump snow into the water tank. If the hot water drill goes offline before it's finished drilling a hole, the water in the hole will refreeze and the operation will have to start all over. So all of this sounds difficult but not impossible, right? You get all the equipment down there to the South Pole, you get the water circuit going, start drilling holes, and you get it done. Except there's another problem. All those boilers heating the water for the drill require a lot of fuel, and at the South Pole, you can only be resupplied with fuel during the summer season. If you're lucky, the summer season runs for 3 months from November to February. The rest of the time, all of the equipment has to be winterized and tucked away in storage, a process which takes 2 weeks by itself. And then the next year, it takes about 4 weeks to get it out of storage and ready to go again. That means, out of the 3-month summer working season, half of it is taken up with setup and teardown. To make use of every possible minute, the drillers worked in 9-hour rotations around the clock. It took them an average of 48 hours to drill one hole, and then they would move immediately on to the next. In all, it took 7 seasons to drill 86 holes and place 5,160 DOMs, but the operation was a resounding success. The IceCube Neutrino Observatory continues to collect valuable data to this day, and is scheduled to be upgraded with more DOMs in the next few years. If you're interested in what IceCube does, along with a little tour of the facility, go check out my other video that explains the science behind it.